In this video, I am going to solve the previous year question papers of ISI Mmath exam. So it is not possible to solve all the problems for me now. Even if I don't know whether I can be able to solve all the problems. But the thing is that I am going to give the idea and try to solve some problems so that you can get some idea that how to approach the problems. Okay, I have already made a video that how to prepare for ISI CMI exam. In there I have already mentioned some books. I can tell you that there are some years when the same direct question from the exercise of the book routine, sometimes from Damit Food or Hoffman Kunz ISI Mmath question comes as well as CMI. So that's why it is very important to solve the exercise, and I can tell you that if you want to qualify this exam, then you need to solve the exercise of these standard books, okay, to get the idea that how to approach the problems. It will enhance your thinking power as well as it will enhance your ability of writing down properly. I know some students that who knows the answer correctly, who have some idea, but writing down in a detailed way, that is very very important. Okay, so that's why it is very important to solve. Okay, so let's try to solve it. I know that the video is going to be very lengthy, but if you can't watch it one time, you just make a pause and one by one you can do that. But still I am going to try to solve some problem. Okay, let's see. So it's dotted, why I don't know, but something is the standard. 2023. So the questions I'm going to solve, it is the questions from 2023 when I was qualified for this exam in the last year. Okay, so the first question which I have solved during the exam, that is basically S is a set XYZ belongs to R3 such that XYZ positive and XY plus YZ plus ZX equal to 1. Prove that there exists a pair of three elements like ABC belongs to S such that ABC greater equal to XYZ for all XYZ in S. So observe, we have XY plus YZ plus ZX equal to 1. And we have to do something called XYZ. What is the first obvious choice we can do? That is AMGM inequality, right? So apply that. And what will you have? XY plus YZ plus ZX divided by 3, that is greater than equal to XY times YZ times ZX or 1 by 3, which is same as 1 by 3 because XY plus YZ plus ZX is 1 by 3 greater equal to XYZ times 2 by 3, which is same as 1 by 3 root 3 greater equal to XYZ. Hence, for all XYZ belongs to S, XYZ is less equal to 1 by 3 root 3. Now observe, let A equal to 1 by root 3, B equal to 1 by root 3, C equal to 1 by root 3. Then we get ABC equals to 1 by 3 root 3. And also AB plus BC plus CA, which is same as 1 by 3 plus 1 by 3 plus 1 by 3, which is 1, right? That will imply that this pair belongs to S, which is implied that XYZ less equal to ABC. Proved. It's a very simple problem, right? It's a very simple problem. Okay, so it's just application of AMGM inequality. Application of AMGM. Right. Go to the next one. The next problem that I have solved, it is also 2023 problem, that show that show that x to the n is solution of the differential equation y double dash plus pxy dash plus qxy equal to 0, where px, qx non-zero polynomial, px q is non-zero polynomial, on -1, 1 if and only if n equal to 1. It's a very simple problem, just computation. Okay, so what I did, let px equals to a0 plus a1x plus a2x square plus dot 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 ak x to the k, because px is a polynomial. Qx is equals to b0 plus b1x plus dot 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 bt x to the t. If I take that x to the n is a solution, I have to show that if and only if case. Okay, so let n equal to 1, then y equal to x, y prime equal to 1, y double prime equal to 0. So in particular, if I choose px to be x and qx to be -1, then 0 plus x times 1 plus -1 times x is 0, which is imply that y equal to x is a solution. So one part is done. Conversely, let y equal to x to the n is solution, right? Then y dash equals to n x to the n minus 1, y double dash equal to n into n minus 1 into x to the n minus 2. If I write down properly, we have n into n minus 1 x to the n minus 2 plus a0 plus a1x plus akx to the k times n into x to the n minus 1 plus b0 plus b1x plus bt x to the t times x to the t times x to the n equals to 0. Now observe, you can see that here the terms start from x to the n minus 1. Here the terms start from x to the n. So comparing the lowest degree term both sides, we get n into n minus 1 is 0, because here the lowest degree term is x to the n minus 1 and here the lowest degree term is x to the n. So in this sum, the lowest degree term is x to the n minus 2. So that means that coefficient must be 0, because here on the right hand side we have 0. That means n into x to n minus 1 is 0, which will imply n equal to 0 or n equal to 1. Let n equal to 0. That will imply that y equal to 0, then y dash to y double dash equal to 0. Double dash equal to 0. Is it asking about non-zero solution? Check. Zero solution is always there. Oh, sorry, if n equal to 0, that means y equal to 1, right? Because x to the 0 is 1. That means y dash and y double dash x equal to 0. That means 0 plus 0 plus qx times 1 equal to 0. That means qx is 0 identically. But it is given that qx is non-zero. Hence that is a contradiction. Okay. Right. Hence let n equal to 1. That means y equal to x. Then n, other part I have already done. So n equal to 0, it will contradict. So that means n equal to 1. Hence if and only if it is done. Right? That means this part is also done. Okay. Then come to the next question. The next question says that is also 2023 question. Okay, this one is also I did. The T is basically RT to RT be a linear transformation such that T power m such that T show that it is given that it's T power m RT is basically same as T power D RT for all m greater or equal to D. So in this question I did this in during the exam, but I did a different approach, and which is very lengthy and very difficult. So that was not a good approach, but it was correct. I take some minimal polynomial of t and give some argument. That is actually the same argument, but it's in a different way, so that it becomes lengthy and different. But I can give a easy argument which I understand after coming back to home, when I think about this question paper, and then I realized that I can do it in a very easy way. Okay, so see you can easily see that kernel of t is always contained in kernel of t square, right? Because it is obvious that tx equals to 0, that will imply that t square x equal to 0. So in this way I can write it, it is inside kernel of t cube dot dot dot, it is inside kernel of t to the power d, right? Now observe that kernel of t to the power k is inside r to the power t. That is imply dimension of kernel of t to the power k for any k is less equal to d for any k, right? That means here is the thing. You have this equation, right? You have this equation. Now even if the inequality is strict, even if all the inequalities are strict, then also you can see that kernel of t to the power d becomes d, dimension of kernel of t to the power d becomes d. Why? Because say kernel of t starts from 1, say if it is starts from 3 or 4 or 2, then it is definitely happen, but I am starting say kernel of t is 1. If it is strictly proper, then kernel of t square is at least 2, then kernel of t cube is at least 3. In this way kernel of t to the power d is at least d, but it cannot exceed d because that is a subspace of r power d, right? So in particular you can say that kernel of t power d is d, right? It might happen that kernel of t power 3 can be d, but if that is true, then that is inside kernel of t power 4, and kernel of t power 3 is rd if, I'm just writing it in this way, if you can't understand, please comment there. So if kernel of t power 3 is d, say, okay, dimension, then kernel of t cube is always inside kernel of t power 4, and that is that dimension of that is less equal to dimension of that, but that dimension is also less than d. Here is d, that means this one is also d. That means similarly kernel of t power 5 is also d, and so on. So in particular, if the inclusion is strict, then also kernel of t to the power d dimension is must be d. So that will imply kernel of t to the power d dimension of kernel of t to the power d is d, even if this is strict. And if it is not strict, then at some point it will be same. That means the easy obvious thing is that kernel of t to the power d is same as kernel of t to the power d plus 1, because, right, kernel of t to the power d plus 1, because if the inequality is strict, then also it becomes the whole space, and then kernel of t to the power d plus 1 must be that whole space. But if the inequality is not strict, then it somehow in between it stabilizes, say kernel of t power 3 is same equal to something like that, right? Then also it will hold. If this holds, that will imply kernel of t power d plus 2, and so on. That will imply kernel of t power m, right? right? Now again, this will imply dimension of image t power d is same as dimension of image t power m for all m greater or equal to d. Fine. So dimension of image t power d is same as dimension of image t power m, right? So this I have a like I got this that dimension of image t power d is same as dimension image t power m for all m greater or equal to d. Now claim it is obvious that image of t power m is always contained in image of t power d where m greater or equal to d. Why? Because say y belongs to image t power m, that will imply that t power mx equal to y for someone. We can write it t power d t power m minus d x y, which is basically same as t power d times some w y, which is implied y belongs to image t power d, right? So this one is subspace of this one and their dimension is same, that means they are identically same. Will imply image t power m equal to image t power d m equal to d. Done. Okay, right. Now go to another question. It was given that this is also 2023 question I solved. This was the first question I solved because I like group theory, so I started solving with group theory. But there are the first two problems were a little bit easy, but then also I start with this because I like group theory well. Okay, so let G be a finite group having odd number of elements. Okay, A be an element of order 3 such that cyclic, such that this is obviously cyclic, but A is the element of order 3 and normal. It is given normal. Show that A belongs to ZC. That means A is in center. So proof. Observe that given that this is normal, this will imply fix G belongs to Z, G A G inverse equal to identity or A square. G A G inverse equal to identity, that will imply G A equals to Z, that will imply A equal to identity. This is a contradiction because A is the element of order 3. G A G inverse equal to A, that means G A equal to AG. We are done, right? We are done because A commutes with G. But if G A G inverse equal to A square, then what is going to happen? That we need to check. Right, so if G A G inverse equal to A square, that means G A G inverse times G A G inverse, which is basically A power 4, which is same as G A square G inverse is A power 4. But A cube is identity, that means it is A. Right? That means it is A. Again, if I put A square equal to G A G inverse, that will I will get G A G inverse times G inverse equal to A, which is same as G square A G power minus 2 equal to A. Inductively, we get G power 2n A G power minus 2n equal to A. Now order of G is odd. Order of G divides order of G. order small g divides order of g by Lagrange's theorem, so that will imply that order of g is odd. Let's assume that order of g is 2n plus 1 for some n. I can see that g power 2n a g power minus 2n is g power 2n a g power minus 2n is basically a for all n, right? So now g power 2n plus 1 times a is basically a into g power 2n plus 1, because it is identity, so a equal to a, so this includes, right? Now g power 2n times a is basically a times g power 2n times g. Again, we know from the previous case that g power 2n times a is basically a times g power 2n, which is same as 8 times g power 2n plus 1. Again, g power 2n is basically same as a, because g power 2n plus 1 is identity that we have already assumed. Multiply with g both side, ag. Again, g power 2n plus 1 is identity, so that means g equal to ag. Hence, a is in center. Proof. Because we can show that if g inverse is a square, then also g equal to ag. It's done. Fine. 4 questions I have solved already. So solution of question number 5. This was a very easy problem. That let PQ be two distinct odd primes such that P minus 1 divides Q minus 1, and if n is co-prime to PQ, where n is a positive number, then PQ divides n power Q minus 1 minus 1. So it is basically application of Fermat's little theorem, which is very obvious. So see, the thing is that n is co-prime to PQ. This will imply that GCD of P comma n equal to 1 and GCD of Q comma n equal to 1, right? That means since GCD of P Qn equal to 1, that means Q power n minus 1, sorry, not Q, n power Q minus 1 is congruent to 1 mod Q by Fermat's little theorem, right? That means Q divides n power Q minus 1, number 1. Again, P minus 1 divides Q minus 1, that will imply Q minus 1 equals to K times P minus 1. Again, by Fermat's little theorem, n power P minus 1 is congruent to 1 mod P. If I multiply the same thing by K times, then I will get n power K into K plus 1 is 1 mod P. That will imply n power Q minus 1 is congruent to 1 mod P, which will imply P divides n power Q minus 1, 2. Now since P and Q are distinct prime, which both divides n power Q minus 1, which implies that their product, because their LCM is basically PQ, divides n power Q minus 1. Okay. So these are the 5 problems from 2023 I have solved. Okay, now I'm going to solve some other problems. Okay. Let's check the question. Let's see. Okay, there is another nice problem from group theory. I think this problem was from, if you need any solution of any question, you can just ask me, no problem. But just try to give. So this one is 2017 problem, I think, which is easy, but I'm just going to give the idea. V finite dimensional vector space over a T from V to V linear map. W is a subspace of V such that TW is inside W, given that T is diagonalizable. Then the question is, T restricted to W is diagonalizable. Okay, so solution. V is a finite dimensional vector space and T is a linear map. Then T has a minimal polynomial. Right? T has a minimal polynomial. Say Px. That will imply that Pt equals to 0 operator. That will imply Pt of V equals to 0 for all V in capital V. Now if I restrict T to W, I get that Pt of W is also 0 because it is true for all V. In particular, it is true for any element in W. That will imply that now if I can consider that let Qx be minimal polynomial for T restricted to W, this will imply that Qx must divide Px because Px is a polynomial such that Pt equals to 0. Pt restricted on W is equals to 0. That means T satisfies the polynomial P, and Qx is the minimal polynomial for T restricted to W. By property of minimal polynomial, it must divide Px, right? Okay. Now we know T is diagonalizable if and only if minimal polynomial Px is product of distinct linear factors. Distinct linear factors. Right? So T is diagonalizable if and only if minimal polynomial Px is product of distinct linear factors, which will imply that Qx is product of distinct linear factors. Which will imply T restricted to W is diagonalizable. Right? Simple problem by just using the properties. Okay. So That's why I ask you to think about it, that the problems are not difficult. If you know the result, you know all types of result, you can solve it. Okay, let's try to solve some other problem. Okay, so the problem, need to check which one. Right, this was I think the problem of 2028. Now the problem number 7 is actually exercise of routine. Their hint was given, so directly the exercise of the routine comes. Okay. It says that f from 0 1 to r be a real valued function which is differentiable on 0 1 and satisfies f0 equals to 0. Suppose there exists c belongs to 0 1 such that mod f prime x less equal to c times mod fx for all x in 0 1. Then we need to show that fx equal to 0. Okay. So solution. So fix x belongs to 0 1, any x belongs to 0 1. Okay. fx minus f0 basically f dash x1 times x. f0 is 0, that means fx equal to f dash x1 times x. That means mod fx equal to mod f dash x1 times x, which is same as c into mod f of x1 times x. Now x is itself less than 1, less equal to 1, right? So it is basically c times mod of x1 1. Again, f of x1 minus f of 0 is basically f prime x2 times x1. So mod of f of x1 is less than f prime x2 times x1, which is same as saying c times f of x2 times x1, which is same as c times f of x2. This is 2. So from 1 and 2 we get mod of fx less equals to c square mod of f of x2. Now if I do the same process after repeated process by inductively, I have fx less equals to c power n mod f of xn, right? Now f is 0 1 to r is continuous. That will imply that mod fx is less equal to m of some m, because f must be bounded on closed interval, closed bounded interval. Continuous function on closed bounded interval must be bounded. We know that. That will imply mod fx less equal to c power n times n. Now I can do n. Now if n goes to infinity, c power n goes to 0, as c belongs to open 0, open 1, which will imply fx equals to 0. Now you can start with any x and do the same thing. Okay, and in particular f0 is given to be 0. That's why you can choose any x greater than 0 which is in less equal to 1 and do the same thing. That will imply the fx equal to 0. Hence fx equal to 0 identically. This is actually a direct exercise from Gooden's book. It's not a difficult thing. Basic results. You have to see that all the questions that I have solved already, it just requires some basic results. Nothing more than that. So that's why you can, if you understand theorems, results properly, you see the proof, you can directly solve that. Problem number 8. It is also 2018 problem. It's a lengthy problem. F equal to g to c, but the problem is easy. Function. Then it has 3 parts. Part 1. Show that for all h in G, summation fg, G belongs to Z, equal to summation G belongs to G f of hg. Okay, by the G, order of G is n plus abelian is given. Okay, right. So C, I can define phi of G equal to hg. Since G is a finite group, you can easily see that hg1 equal to hg2 implies g1 equal to g2. That means it is injective, and finite group means decided. We just said theoretic now. There is no use of homomorphism here. Just set theoretic bijection. Hence, this f of hg is basically permutations of f of g. You just permute it, right? That's why the sum is same. Hence, summation fg equal to summation f of hg. B. Let sister be a multiplicative group of non-zero complex number and G, f is G2. See the homomorphism. G is the given same thing. Okay, sister is homomorphism. Homo. Then I need to show either summation fg equal to 0 or summation fg equal to n. Okay. So this is a homomorphism, right? It means image f is a finite subgroup of sister. Now we know finite subgroup of sister is cyclic. General statement I just want to mention. I'm not going to prove it because that would require some argument, but it's easy proof. You can try. Maybe I can make a different video for particularly this property. This is a very nice property that any finite subgroup of a multiplicative group of field is cyclic. Okay, so that's why C is a field, so sister, any finite subgroup of sister is cyclic, right? That means now order of G is n. That will imply if G power n is 1 in sister, okay. Now if image of f is have order D, that will imply that if image of G, image of f is order D, that means fg power D is 1, right? That will fg is dth root of unity, right? Since image is cyclic, then either g equals to 1 for all g in G, or fg is a non-trivial dth root of unity, right, for some g. Then since the image is cyclic, that means it will generate other dth root of unity also, right? That means hence summation of g belongs to g is basically sum of dth root of unity. That is 0. Okay, if there is not non-zero element, and if there is not, if fg is trivial, if fg is trivial, if f is trivial, then fg equal to 1 for all g belongs to z, then summation fg is summation 1 g belongs to z. That means n, hence either n or 0. Think why sum of dth root of unities. Why? Because you can see that x to the power d minus 1 is 0. From here you can conclude the sum of dth root of unity is 0. Right? Hence we are done. That was one nice question. And there is also something for C part. C part is also obvious. It is basically, I'm not going to tell, it is just same argument. Is any homomorphism, you can just try from that, easy. Then summation mod fg, g belongs to g is n. Because see, fg is a nth root of unity, because fg power n is 1, fg is nth root of unity, right? That will imply mod fg equal to 1. You are summing all the over elements of g, and order of g is n. That means its sum is n. It's easy to see. Okay. There are many other questions also which is doable, but I am not going to do that because try to solve some as much as I can, because otherwise it's very lengthy. Okay. Any other question? Let's see. Question number 9. M be a symmetric matrix of real entries such that m power k is 0, then m is 0. We have to show, right? So we know any real symmetric matrix is diagonalizable. Any real symmetric matrix is diagonalizable. So that will imply m equals to p d p inverse, where d is a diagonal matrix. So m power k is basically p d power k p inverse, which is equals to 0. That will imply d power k is 0. D is a diagonal matrix. D power k means it is lambda 1 power k, lambda n power k, which is 0. That will imply lambda I equals to 0. That will imply d equals to 0. That will imply m equals to 0. Which is easy. It's a 10 marks problem. There's another problem. Let G be a non-abelian group of order PQ, where P less than Q and PQ primes. We need to find how many elements of G has order Q and how many elements of G has order P. Okay. So the thing is that okay. So we need to use Shiloh's theorem here. So number of Shiloh P subgroup is basically 1 plus Pk that divides Q. That means NP equals to 1 or NP equals to Q. And number of Shiloh Q subgroup, that is 1 plus Qk, that divides P. That will, and since Q is greater than P, that means 1 plus Qk is greater or equal to, 1 plus Qk divides P, that will imply that NQ equals to 1, K equals to 0. Otherwise it's not possible, because if K is at least 1, then that means 1 plus Qk is greater or equal to 1 plus Q, which is strictly greater than 1 by P. So that is not possible. So hence Shiloh Q subgroup is exactly 1. Now any subgroup of order Q is cyclic, right? That means if it is H is isomorphic to ZQ. That means number of elements of order Q equals to Q minus 1. Again, let NP equals to 1 and K be Shiloh Q P subgroup. Okay. By Shiloh's theorem, NP equals to 1 as well as NQ equals to 1. That will imply that H and K both are normal, because unique subgroup is not, unique Shiloh P subgroup is normal, right? H and K both are normal, right? Again, H has order P, K has order Q, or vice versa. So that means H intersection K has order 1, because that should divide both the order of H and order of K, but since GCD of PQ is 1, so order of H intersection K is 1. That means H intersection K is identity. Again, order of HK is basically same as order of H times order of K divided by 1, which is PQ, which is same as order of G. That will imply HK equals to Z. I've already made a video for IIT exam solution. There I mentioned the same proof of this theorem. This is the internal data product theorem. If G equals to HK and HK are normal such that order of H intersection order of K is 1, identity, that then G is isomorphic to H cross K. Okay. So here that is happening. If that is happening, that means G is isomorphic to H cross K, which is implied ZP cross ZQ, which is implied ZPQ. It is contradiction because G is given to be abelian. Hence, number of Shiloh P subgroup is exactly Q. Again, let H1 and H2 be distinct Shiloh P subgroup. Order of H1 equal to order of H2 equal to P, means order of H1 intersection H2 equal to 1, because order of H1 intersection H2 must divides P. which is either 1 or p, because since p is a prime, so order of h1 intersection h2 is has order p. That means h1 equal to h2, which is not possible because I am already assuming that it is distinct. That means h1 intersection h2 is trivial. Okay, so that means h1 has p minus 1, sorry, h1 has p minus 1 elements of order p, h2 has p minus 1 elements of order p, and all the elements are distinct here because any two distinct shall be subgroups intersects just trivially, so there is no common element. So there are exactly q many subgroups. It's hq p minus 1. So total number of elements of order p is basically q into p minus 1. Again, there is another problem that comes that I already make a solution, that if the same idea, if I don't recall that exactly the same problem or not, but you can see the other video. So if C is a subset of a compact matrix space such that every continuous function h from x to r attains maximum on C, then C is compact. Okay, C is a compact matrix space. C be a subset of a compact matrix space such that every continuous function attains maximum. If it further restriction not, then it is compact. It's easy one. Although there is a problem related to that there doesn't exist any real valued function such that it takes each value exactly twice. That I have already solved. There is another problem related to the boundedness that I already solved. So let's see. There are some problems. I can just give an idea of some extra. Another one problem. It is given that a from R to R continuous function such that limit x goes to infinity fx equals to limit x goes to minus infinity fx, which is 0. Then we need to show that f is bounded on R and f attains a maximum or a minimum. Okay, so I just gave a partial solution, and you can just comment the solution, the other part solution. Okay, it's easy, but you can visualize its graph so that you can easily understand that what is going on. So observe the limit x tends to infinity fx equals to 0. That means there exists m greater than 0 such that mod fx less than 1 for all x greater than equal to n. And again, limit x tends to negative infinity is fx. Negative infinity fx is 0. That means there exists n less than 0 such that mod fx less than 1 for all x less equal to n. Okay. Now observe this interval is compact. That means f is bounded on Nm. Right. Say mod fx less equal to some u for all x belongs to n comma n. Okay. Or not u, say p. Let k equal to maximum of 1 comma p. It will imply mod fx less equal to k for all x belongs to R. That will imply f is bounded. Now the thing is to draw a picture. You can see that it might be in this way or in that way. You can just see that this kind of thing can be happen. This kind of thing can be happen, but ultimately it goes to 0, right? Both sides. Someone can conclude that it must attain at least one maximum or minimum. Okay. it may not attend both, because if you can see this, the bell shaped graph, okay, both tends to 0 but not goes to 0. Maybe it has no maxima here, but there is no minimum, because minima is 0 but 0 is not attained. So either maximum or minimum must be attained. It is not possible that nothing is no, either maximum or minimum, nothing is that you can see geometrically. But I want reverse one. You can just comment. Okay, this is not a difficult one. Okay, so these are the types of problem that I am to solve. There are other some problems which is easy, and also there are some problems which is difficult. So you may ignore that because it is not important to solve all the problems. But I will tell that at least try to get some idea that what is going on and what is the important result, how to solve it. Okay.